Can you hear us?
Yeah.
Okay. Sorry for wasting your time with witty banter. Maybe, well, witty on your part, maybe not mine. So we're going to talk about various methods of catalysis today. Hopefully we'll get to proton transfers as catalysis. But we're going to talk about a few general methods just so that you can recognize these as they appear in the literature. There's actually not that many unique ways, that we'll talk about in this chapter. As I said, organometallic catalysis is really way outside of my wheelhouse, so we may not talk at all about it because I don't have anything useful to tell you. But Dr. Michaelis does, and so does Dr. S., and so feel free to talk to them if that's your area of interest. So binding something by a Lewis acid, in general, used to stabilize a negative charge that's developing in the transition state. This tends to matter more when you're in organic solvent, a solvent that can't in and of itself solvate negative charges very well. Even though enzymes do their work in aqueous solvent, their active sites in many cases are fairly organic in nature. They're not exactly like bulk water. The dielectric constant is different inside the enzyme than in water. And so stabilizing a negative charge inside an enzyme can be a useful way of accelerating a reaction. So the classic example of this kind of approach is the so-called oxyanion hole, and this is an area in many active sites of enzymes where amide protons, I don't know what we're doing here, sorry, amide protons are clustered. Usually there's 3 of them, and they're clustered in an area that is aligned with where a negatively charged oxygen from a tetrahedral intermediate is going to be. So here's your ketone, here's your nucleophile, and attack of the nucleophile is made easier by the fact that the negative charge is going to be stabilized by all of these partial positive charges that are already in the right place to basically solvate the negative charge. All right. And so that's an important aspect of many enzymes. Many of the proteases and the lipases involve that kind of thing. If you want to see an example of it, just Google oxyanion hole, and you can see it's like this little oxygen-shaped thing where the oxygen from the tetrahedral intermediate should be. Similarly, there are analogs to this even in the lab. So does anybody know how diisobutyl aluminum hydride works? It's kind of weird because it doesn't look like your typical hydride delivery reagent because it's neutral, right? What happens first is Lewis acid, Lewis base. So I don't know that this is a classic example of catalysis because I think the reagent is consumed, but the idea is that you can activate a carbonyl towards reaction by having the carbonyl oxygen interact with a Lewis acid, and then the hydride gets delivered and the ketone's reduced. Anyway, except I don't know, I can't remember. Didn't we say dibol chem stops at the what? I forget. Stops at the aldehyde. So I don't know what it does with ketones, so I'm going to put an ester here so that we can pretend that this is all fine. All right, Lewis acid binding. There's some more elaborate examples. Metals are often included in reactions simply to be Lewis acids. So an example of this is a cobalt complex So I don't really know much of anything about inorganic chemistry. Apparently in inorganic chemistry it is fine to draw bonds from heteroatoms to metals without putting formal charges on heteroatoms. And I'm uneducated in that area, so I apologize. I'm using dotted lines just because it makes me feel better. I've heard of things called dative bonds, but I don't even know what they are. So, confessions of ignorance. All right, so here's a cobalt complex, and it can accelerate the hydrolysis of amino esters. So here is the carbonyl of an ester, and here is the amino group, which can, I'll just draw a line so we're not confused. And even though we're not drawing a formal charge on that oxygen, it should be clear that binding the Lewis acid should polarize the carbon-oxygen bond even further, having more of a positive charge on the carbonyl carbon. Another way of thinking of this is it can also lower the LUMO in energy, and so that facilitates attack. Another use for Lewis acids is to make it possible to get larger concentrations of hydroxide than are actually possible at neutral pH in the absence of the Lewis acid. So I'm going to attempt to draw for you a zinc complex that's encircled by this cyclic polyamine. I forget what cyclic polyamines are called. Yeah. And then there's another one here. Okay. Basically, zinc in 2 plus can bind water, and in so doing lowers the pKa of this proton to be around 7.2. So then it becomes easy for that water to lose its proton even at neutral pH, and then you've got a fair amount of basically negatively charged hydroxide that is available to do chemistry. Presumably, in order for it to do chemistry, it would have to ultimately leave the zinc, and the extent to which it does that might limit its or accelerate its usefulness as a catalyst. But that's in many cases, if you're doing a reaction like a saponification that involves hydroxide and you're adding a metal, one of the things you may be doing is to just bump up the amount of hydroxide you can have in solution while maintaining a more neutral pH. Yeah?
Maybe I'm just confused. So when it had the hydrogen, shouldn't have been positively charged, and then it loses the hydrogen, it's neutral, and then it leaves the zinc, it's hydroxide?
Yes, but we're doing the weird thing with inorganic complexes where
We're pretending the bond is like ish. It's coordinated.
coordination.
Okay.
All right, yeah, and beyond my expertise. I'm really sorry that I don't understand that. Let's see. So another example of things. So that's Lewis acids. Anything else we want to say about that? A lot of examples of these in the literature.
Josh, do we consider like magnesium as a cofactor in the body to be like Lewis acid catalysis?
Sure, I think so. I mean, ATP is mostly bound to a divalent cation magnesium, and surely that's got to facilitate leaving group ability. I don't know of any. I haven't read any experiments that demonstrate that, though I'm sure there are some. Yeah. And the principle is stabilizing negative charge or buildup of electron density. Anything else on that? So we've already talked about proximity as catalysis, though mostly in terms of intramolecular reactions, which is cheating because basically you do the synthesis to make the two things close to each other and then they react. What people would really like to do is to be able to design catalysts that can enforce proximity between two different groups and get chemistry to happen. So here is a designed catalyst from I think 2000. This was published in Chemistry, a European journal, which isn't as fun to say as the European Journal of Organic Chemistry, or EURJOC. That's kind of fun to pronounce. The authors designed this catalyst as an artificial acetylcholine esterase. They're probably overselling it because their substrate is not acetylcholine. Nevertheless, if this were an acetyl group instead of a paranitrophenyl carbonate, it would be, that's like saying if you're, well, anyway, yeah. So they designed this molecule. This is, I think, a Calixorin, and the way it is attracted to the tertiary or the tetrasubstituted tetraalkylammonium group via cation pi interactions. Notice that these arenes are stitched together through CH2 groups, and they're substituted with electron-donating T-butyl and methoxy groups. And basically, because of sterics, they're not flat. They adopt this sort of cone-shaped, bowl-shaped structure into which the tertiary ammonium group can pack. And then appended to one of the rings via an amide linker is this guanidinium functional group, which has two different electron-poor nitrogen-hydrogen bonds. So this is sort of its own oxyanion hole. It comes with a binding site. This is a mini active site. It comes with a binding site and its own oxyanion hole. And the idea was that and now they're going to draw their Calixorin as a little bracket because that's less space. So they found that you could accelerate the methanolysis of this paranitrophenyl carbonate using methoxide by having this artificial catalyst with the guanidinium group coordinating and the hydrogen bonding with the oxygen, stabilizing the negative charge in the tetrahedral intermediate. They could accelerate that process by about 150-fold, which is, I don't know, Mario, do you remember any of I don't know this off the top of my head, but in any of David's work with helical peptide catalysts, do you remember how much acceleration there was relative to? I think it was thousands. Although you could argue, well, that you're doing it at such low concentration that, but in any case, this is sort of small potatoes for catalyst, but this was an early example of a organic molecule using classical principles of supramolecular chemistry and non-covalent interactions that did something. Yeah.
How did they decide that it would? Because it kind of almost, maybe it's the 3D geometry that I can't envision. It almost looks like it's kind of like a crown ether, where you
Yes.
assume that the thing is coordinated with the oxygen, not with the pi system.
Oh, I don't know how they verified. Presumably, there were previous crystal structures showing that calixorines could bind cations, and so and perhaps they had a crystal structure of acetylcholine bound in it. I don't know.
Showing that it's interacting with pi systems now.
Yeah, and I don't know I don't know if there were any crystal structures or not. The reference is actually in one of those connections boxes in your text, so you can look at that. The binding constant between the paranitrophenylcholine carbonate is 6 times 10 to the third per molar, And if you ever want to know how good a binding constant is, that's the association constant. It's always useful to take the reciprocal of that, which is the dissociation constant, which has units of molar. So 1 over 6 times 10 to the third, that's in the millimolar range. And that gives you a sense for how concentrated your substrate has to be in order to bind the molecule. So millimolar binders are not typically that good. We'll talk about enzymes though, and binding isn't necessarily the whole story with enzymes. It's not clear that making something bind as tightly as possible is the desired thing for enzymes. So anyway, yeah.
Yeah, if it binds super tight, then it may not be able to come off.
That's right. You need, for enzymes to work and turn over, the thing needs to be able to dissociate from the enzyme, and so you have to be careful. Ideally, if you optimize binding for the transition state, then once you form product, you don't fit as well anymore, and that makes you hop out of the active site. Okay, so we've done Lewis acid catalysis. Now we're going to do Lewis base or nucleophilic catalysis. The classic example of this is in activation of acid chlorides and other carboxylic acid derivatives for nucleophilic substitution. So here's some leaving group, maybe an acid chloride. And suppose you wanted to add, we're doing way too many R groups. So suppose you wanted to make the methyl ester. I don't know why, and there's easier ways to make the methyl ester. So, okay, fine, we'll say the ethyl ester. Supposing you wanted to make the ethyl ester, you're in kind of a pickle because ethanol itself is not that great of a nucleophile, but if you add a strong base like hydroxide, maybe you're going to have hydroxide attack the carbonyl carbon. So one of the things people do is they put a catalytic amount of a molecule that should be more nucleophilic than the thing you want ultimately to replace the leaving group. So carbonyl, you attack the carbonyl carbon, you get to this molecule, and even though the nitrogen, the tertiary nitrogen or the trialkyl nitrogen is more nucleophilic than the alcohol, you stick it on the carbonyl and now it's an even better leaving group, or it activates the carbonyl it makes the carbonyl way more electrophilic because now you have a positive charge adjacent to something that's already electron poor. So now it's super activated, and you can now have your alcohol do the attacking and ultimately get to your ester product, and your trialkyl amine is regenerated. So this is used in a lot of amide bond forming reactions, and a lot of peptide coupling reactions actually use amino or other kinds of additives to make carbonyl compounds more electrophilic. One that's often used is dimethylaminopyridine, or DMAP. Anybody use that? What have you used it for? Okay. And the nucleophilic nitrogen is which one? The one that I drew the lone pairs on, right? Yep. Good. So if that were bonded to a carbonyl carbon, again, it would be positively charged. 4 bonds to nitrogen. Very good leaving group, and that can help with the next step that needs to happen. All right. Another one that I didn't know about for nucleophilic catalysis is you can actually use nucleophiles to make super Lewis acids, or maybe by super I mean just really the idea here is, suppose you have some donor with an orbital, D is for donor, with electrons in a high energy orbital, and then you have a Lewis acid or acceptor with a low energy empty orbital, and the Lewis acid is attached to, in this case we'll pretend it's like boron or aluminum, 3 different things. We're all sort of used to the idea of making a new bond between A and D, or having electrons from D attack and fill an empty orbital in A. Here I'm not showing formal charges, though presumably there would be a positive on D and a negative on A. And what this can sometimes do is it can induce a ligand to leave from A, so that you now have and I think the arrow here represents sort of a coordination type bond, but you now basically have a supercharged Lewis acid in whatever, and I somehow switched from A to aluminum. I'm very sorry. All right. So I haven't seen actually a lot of examples of this. This was new to me. Do any of you know of any reactions you've done before where this has been a thing? The one example that the book gives is of this chiral phosphoramide. Nope, it was R2 there. I think probably I'm just going to put binap here. It's a chiral binaphthyl attached to those nitrogens because I don't want to draw it. The authors added silicon tetrachloride as a Lewis acid, and the carbonyl oxygen interacts with the silicon and causes one of the chlorines to leave, so that now the silicon is even more Lewis acidic. It's like you take something that was teetering on the edge and you bump it a little bit, and one of the leaving group leaves, and then it becomes even more electrophilic. And this complex presumably, your text says activates aldehydes to attack, and because of the chiral nature of the binaphthyl group, you can get stereoselectivity. All right, questions about that? So your text calls the next thing covalent catalysis, but because the catalyst forms covalent bonds with the substrate. But I think a more current term is organocatalysis. And this began in the late 90s and early 2000s with the idea, can we imitate nature with small amino compounds to catalyze reactions involving imines and enamines? So an example is, and this field was small at first, but then sort of exploded, and there's tons of organocatalysts now. They tend not to be as efficient or have as high turnovers as a lot of the organometallic type catalysts, and so it's still a developing field. This is a beta ketoester, and as many of you learned in 352, under strong acidic conditions and with heat, you can decarboxylate to get the ketone. But not all molecules can withstand strong acid and heat. So being able to perform this reaction under at room temperature and with more neutral pH is desirable. And, or maybe instead of neutral pH, we'll just say less acidic. What happens when you bring this amino group in the presence of the ketone is you form the iminium species first, and the iminium acts as an electron sink because it's a place for the electrons to go, for the electrons in this bond to go as CO2 leaves. So here's the decarboxylation. Electrons move over here and then up onto the iminium nitrogen, which is now in the product neutral. And so you end up with CO2 and then this enamine, except I can't spell. And then you can hydrolyze the enamine with water to generate your ketone and then regenerate your catalyst. So this is iminium chemistry, and it's used a lot to activate electrophiles. Yeah?
So the positive charge on the nitrogen is what allows that terminal carbon to be oxidized to CO2?
Yes, although I mean it's a oxidation / reduction, I guess. In this, it's not a. I suppose it is a change in oxidation for this carbon. Then it should also be a change in oxidation state for this carbon, which gets reduced from a carbon-carbon bond to a carbon-hydrogen bond.
Yeah, or for the nitrogen, which.
Yeah, although the nitrogen can pop off. Unchanged, so what's really sort of changed is this carbon.
Okay, so in the end, the nitrogen comes back off.
Yep, and that's why it's a catalyst. Yeah, in the end, the nitrogen comes back off. The enamine can be hydrolyzed easily. A lot of why can't I say it? A lot of organocatalysts work through iminium chemistry, and some work through enamine chemistry. You can use enamines as nucleophiles. I'll show you an example that was included, I think, in your text. This is the work of David McMillan, who's one of the founders and authors of the organocatalysis field. And he generated a chiral catalyst that can perform conjugate addition reactions in good yields and great enantioselectivities. For those of you playing along at home, the catalyst is derived from the amino acid phenylalanine, and then I'm not sure how they generate that. And there are a number of different things that are called Macmillan catalysts. With a little bit of acid, you can catalyze formation of the iminium ion, which again, because it is positively charged, is more reactive than the aldehyde was, and therefore a better substrate for attack by a nucleophile. Your text says that this is a much lower lying LUMO, in part because of the positive charge on the nitrogen. And so this facilitates a nucleophile coming in and attacking at the beta carbon to give an enamine intermediate, where you formed a new bond between nucleophile and the beta carbon of the alpha beta unsaturated iminium ion. And I believe in this case the nucleophile attacked from below. The rationale for that is, I think, that the top face of that enone should be fairly sterically crowded. And then with again, the existing acid and water that's present in solution, you can regenerate the catalyst. And now you've just installed a nucleophile at the beta carbon. Oops. And you've got back your aldehyde. And there are lots of examples of this. The amino acid proline, the secondary amine in proline, can also be a good organocatalyst. And there's a huge field out there for different organocatalysts that promote different reactions. Many of them are aldol type or carbonyl chemistry type molecules. I believe in the Michaelis group, it's something like this. I don't think it's exactly this, but it's something like this that's appended to a helix to activate an enone that's actually much like what's shown here, 4-E-Diels-Alder reaction. All right, so there's tons more to say about organocatalysis, but you can read the literature and take a look. All you have to do is Google organocatalysis and you'll have more to read than you can possibly read in your life. All right. The last step on our journey is to talk about using strain to distort the structure of a molecule along the reaction coordinate to facilitate various chemistry. I could draw this, and maybe I should. Fine. So catalysts can use strain. So the enzyme that's called lysozyme, one of the things it does is it hydrolyzes the glycosidic linkage between the following carbohydrates. It's a beta-1,4 linkage between N-acetylglucosamine molecules, and we can actually look up where lysozyme is. It's a very well-behaved enzyme. If you ever want to learn how to crystallize proteins, lysozyme almost always crystallizes and generates diffraction quality crystals, and its structure is known. So if you want to go do something easy but learn some protein crystallography, many people start with lysozyme. I kind of want to look up Owl City, deer in the headlight. Oh, that's where the Owl City picture came from that was in my list. My children are searching various things. Let's see, lysozyme. Occurring notably in tears and egg white. So yeah, where are lysozymes found in the body? Secretions of lacrimal glands of animals, nasal mucus, gastric secretions, and egg white. So snot is found in tears and snot. And egg whites. What am I searching there? Yeah. I think I was looking up where some actor had been in. Oh yeah. We watched an episode of Brooklyn Nine-Nine with this guy in it, and I recognized him but didn't know from where. It turns out he was in an episode of The Office. So now you know. Okay, so lysozyme hydrolyzes. One of the things it does is hydrolyzes this linkage. And the problem with doing that is if you zoom in on the anomeric carbon, basically you've got your leaving group here. Oops. But the orbitals that are available on that neighboring oxygen include an S-rich orbital that's sort of in this direction and a P-rich orbital that's sort of in that direction. And we haven't talked in this class, we will, but we haven't talked in this class so far about the requirement for leaving groups to be either syn or anti-periplanar to either the lone pair or the proton that's going to get removed to kick off the leaving group in elimination reactions. And the orbitals just don't line up very well. They would line up perfectly if this was an alpha 1,4 linkage. Then the leaving group would be here, and it would line up great with the p-rich lone pair. As it is, you're never going to get any of these lone pairs anti to this leaving group. The best you could do is to try to tweak the ring a little bit to make this S-rich lone pair be more syn periplanar to the leaving group. And so that's what the enzyme does. It basically binds the sugar and tweaks its structure by clashing with the C6 hydroxyl group. And that causes the chair to twist into a half chair, which all I can really do for you there is draw a really bad chair, because I can't draw a half chair. And at that point, because of the steric distortion, now the lone pair is more syn periplanar, and that allows the electronics to work such that you can eliminate the leaving group. And there are other enzymes that work in this way. There are enzymes called peptidyl proline isomerases, and they're designed to, do you remember, I guess, in the last exam how we talked about cis versus trans amides involving proline? In many cases, in protein folding, isomerization of a trans linkage for proline to a cis linkage for proline is one of the rate determining steps for protein folding. And so there are enzymes, catalysts, that actually help distort that structure to enable flipping from cis to trans. All right, your text mentions phase transfer catalysts like crown ethers. I think that's worth looking at, but I don't think it's really worth talking that much about because it's pretty straightforward. So that leads us on to proton transfers. And I got to tell you, it's fun for me. It's always fun when a teacher tells you that something's going to be fun. Proton transfer catalysis. This has been fun for me to learn about because I remember hearing some of these terms in biochemistry, but I never really understood them. And now I understand them a little bit better. So there are going to be two types of proton transfer catalysis. There's specific acid or base catalysis. And then there's general acid or base catalysis. And it's not what you think. That's maybe the lesson I got from it. It's not what you think. So the defining feature of specific acid catalysis is that the acid or base is not involved in the rate determining step, but in a prior equilibrium. Whereas for general acid-base catalysis, the acid or base is in the rate determining step. That's the basic feature. Now, another element of specific acid catalysis is that it involves, surprise, the specific acid. And the specific acid is the protonated form of whatever solvent you're in. So in water, the specific acid is H3O plus. Okay, that is the specific acid in water. It seems a little bit counterintuitive because there's lots of hydronium in water, and so, but if you memorize that we're calling hydronium the specific acid in water, then this gets a little bit easier. Alternatively, the specific base in water is hydroxide. Okay? General acid or base catalysis may involve hydronium or OH, but can also involve any general acid, HA or B. And we'll see how that is a little bit later, but the key thing that distinguishes general versus specific acid is this. The acid is in the rate determining step for general acid catalysis. For specific acid catalysis, it's not, but rather in a prior equilibrium. And that has some very specific mathematical consequences that determine how reaction rates depend on pH. And we're going to learn about that. Any questions so far? The part that's most confusing is sometimes the specific acid, hydronium, can act as a general acid in a general acid catalyzed mechanism. Who you may ask were the idiots that came up with this designation, and I just have to say not it. Sorry. But you will hear people talk about this, but remember when they do that it comes down to a specific kinetic issue. Is the acid involved in the rate determining step or instead in a prior equilibrium? So we're going to start with the math of specific acid catalysis. I'll show you the math for that, and then I won't show you the math for specific base catalysis, but what we do for the acid will apply. So let's set up a situation where that's the case. You have some molecule, R. I don't know why R is our favorite generic thing, and we're going to protonate it with RH. I'm sorry, we're going to protonate it with hydronium to generate the protonated species. And then in a slow step, where we've got the rate constant, the rate determining step of the reaction, we're going to convert to product, and then in a subsequent fast step that we don't see, we'll regenerate hydronium. All right? And because the rate determining step involves conversion of RH plus to protonated R to protonated product, we can say that the appearance of product as a function of time should be equal to the rate constant times the amount of protonated R. Okay. But we may not know at any point in the reaction what protonated R is, but we might be able to follow how much of the original R we have left. And because this is an equilibrium, we can say Ka equals H3O plus times R divided by RH plus. And that is the Ka of protonated R. You with me so far? If you're worried about where water went, don't. It's folded into Ka. So if you wanted to, we could have put water here and K equilibrium constant, but we would have gotten rid of water by multiplying water concentration by KEQ to give us Ka. All right. So then we put that back into this expression to figure out how the rate of our reaction depends on the concentration of hydronium, the concentration of your starting material, and the Ka of your protonated R. I just did a quick substitution for RH. I moved it over here and then moved Ka down there. You okay with that? So if you think about this, Ka is a constant, And if you're running the reaction in buffer, pH is constant. So all of this can be translated into a pseudo first order kinetic setup where K observed equals K times H3O plus divided by Ka. Now let's talk about how we would expect Ka to be influenced by pH. So we'll go from low pH to high, left to right, and then we'll put log of the K obs. We're using logs here, so we're comparing apples to apples. Hydronium minus log of hydronium is pH, and then log of K obs. So what do you expect for an acid catalyzed reaction with the rate constant defined as I've shown you? What do you expect the pH dependence to be? Should be linear, right? I mean, if you look at this equation, it's clear that it's linear. And if you take the log of K obs and the log of K times H3O plus divided by Ka, what this really becomes is constant minus pH. And that tells you that the slope should be linear with slope minus 1. And that's in fact what we observe. That's a characteristic of specific acid catalysis. And there is where we're going to have to stop it today. Next time, we're going to talk about what happens when you use an acid that's not hydronium, but it's still not involved in the rate determining step. And that gets kind of interesting. So stay tuned. Tomorrow is a Pretend Friday. If you're not here, that's fine. I will just record it and broadcast it as usual. Please stay safe and stay healthy. Please don't do stupid things. Anyway. Wear your mask, wash your hands, don't pick your nose at the dinner table. Although I suppose if you do it underneath your mask, then at least they're shielded and nobody sees. So there you go. All right, have a great day.